Hello, my name is Tomasz Idziaszek, and in this video I will talk about a solution to the Code Alone Challenge 2021 powered by Codility. In this challenge, we are giving a string consisting of letters A and B, and we are asked what is the minimal number of swaps of neighboring letters that we need to do in order to obtain in a string 3 consecutive letters A and 3 consecutive letters B. Let's analyze some examples. In this string, we can use 3 swaps to obtain a desired result. We can swap the first B with the second A. Thanks to that, the first 2 A's will be together. And then we can use 2 more swaps to move the last A 2 positions to the left, forming a group of 3 A's, and at the same time forming a group of 3 B's. So we needed 3 swaps here, and we can show in fact that 3 swaps are necessary for this string because we need at least 2 swaps to form a group of 3 A's, and after doing that we still need some swaps to form a group of 3 B's. Therefore, the correct answer for this example is 3. Let's analyze some more examples. In the next one, we'll have some difficulty in obtaining a desired result because we have only 2 letters B. Therefore, we cannot obtain a group of 3 B's no matter how many swaps we will do. And this is a general rule. If the number of letters A in our string is less than 3, or the number of letters B in the string is less than 3, then the answer is -1. We cannot create a desired result. But this is the only case in which task is impossible, because if we have at least 3 A's and at least 3 B's, we can use our swaps to sort the string lexicographically, that is to move all letters A to the beginning of the string and all letters B to the end of the string, therefore forming desired groups. But of course, this sorting algorithm will not necessarily give us the smallest number of swaps. One of the difficulties in solving our problem is that we need to take care of creating a group of 3 A's, and at the same time we need to think about creating a group of 3 B's. So let's simplify our problem for a minute and think what kind of swaps we would need to do if we were only interested in creating one group of 3 letters. That happens when the other group is already presented in our string. So in the next example, we already have a group of 3 consecutive A's. So now our task is to create a group of 3 consecutive B's. So the first question is, what instances of letter B should form the group? And the second question is, what is the minimal number of swaps to move these instances to form a group? If we decide on subset of 3 B's, then the answer to the second question is pretty easy. Here we need at least 3 swaps to remove all the letters that are between the first instance and the second instance of letter B, and another 4 swaps to remove all the letters between the second instance of B and the third instance of B. That leads to a general formula. If the first instance of B is at position X and the third one is at position Y, then the total cost is Y minus X minus 2. But it's easy to see that the cost 7 in this example is not optimal. For instance, when making the swaps, we swap the letter B at position Y with another letter B at position Y prime. And since letters B are indistinguishable, this swap does not make sense, and in fact it will be better to take B at position Y prime than B at position Y as the third letter in the set, because then we will need only 4 swaps to form a group. So we need to only consider such a set of 3 letters B that there are no other letters B between them. So now we can answer the question how to select such a set of 3 B's Well, we can test all possible candidates because we can have another set of three letters B's that are close to each other. That will result in a smaller number of swaps. But this is rather straightforward. First, we make a pass over our string to collect all the positions in which letters B appear. And then we make a pass over vector of these numbers to find the triplet of positions which result in the smallest cost. This part runs in linear time in the length of the string. So we know how to calculate the minimal cost of forming a group of three letters B, but the important property of the sequence of swaps generated by our algorithm is that they don't break the existing group of three consecutive A's. In fact, they can only extend such a group because they will join two groups of letters A previously separated by letter B on position X, and they will join two groups of letters A previously separated by the letter B on position Y. Therefore, we can use this approach for any string in which we already have a group of three consecutive A's. And by symmetry, we can use a similar approach on a string in which have three consecutive letters B's. We just need to switch the roles of letters A and B. Okay, so we have taken care of the simplified version of the problem in which we only care about grouping one type of letter, but we still need to figure out what to do with the case when we have no group of three consecutive letters A, nor a group of three consecutive letters B in the string. So we might think that we are back to the general case in which we need to think at the same time about creating a group of A's and group of B's, but since we have this restriction on the string, this case is not as general as it was before. For instance, we can show that the answer in this case will not be very big. In the previous case, the answer could be as big as n-3 when we had only three letters B and two of them occupy the first and the last position in the string. But this was only possible because of a large number of groups of three consecutive letters A. But now this is not possible. So let's see what is the longest possible fragment of consecutive letters in which we don't have three letters B. Well, this fragment could start with a letter A, followed by another letter A, but we cannot append a third letter A here because then we would have a forbidden substring of three consecutive letters A. Therefore, we are forced to put letter B. Then we can put another two letters A, followed by another B, and two more letters A. So this fragment has length 8, and if we would like to extend it more, then we are forced to put the third letter B. Therefore, if we take any fragment in our string of size at least 9, then we know it will contain at least three letters B, and by symmetry, at least three letters A. That means that we can take any fragment of length 9 in our string, for instance, the first 9 letters, and rearrange the letters in this fragment using not very big number of swaps to produce a group of three consecutive A's and a group of three consecutive B's. Let's assume, without losing of generality, that the letter B appears less number of times than the letter A. Therefore, the letter B appears either 3 times or 4 times. If it appears 3 times, then the biggest number of swaps we need to do in order to form a group of 3 consecutive letters B's is 4, because we can have at most 2 letters A between the first B and the second one, and between the second one and the third one. But after forming a group of 3 B's, we will see that the group of 3 A's will be formed automatically because we have 6 letters A, so either 3 of them will appear before the group of B's or after it. So in this case, 4 swaps will be enough. With 4 letters B, the maximum number of swaps we need to do to form a group of 3 Bs will be 3. And then if no group of 3 A's is formed, that means we have a group of 3 A's with B in the middle, and we can remove this B using one additional swap. Therefore, in both cases, the answer will be no bigger than 4 swaps. Therefore, we can take any fragment of length 9 in our string and rearrange the letters in this fragment using at most 4 swaps to obtain a group of 3 consecutive A's and 3 consecutive B's. So we know that this way we can get some small answer, but the question is it the smallest answer possible? Well, for different fragments of length 9, we can have different costs. For instance, it's not hard to come up with a fragment for which we only need 1 swap. So one could say, let's analyze all fragments of length 9 and return the minimal cost among them. So this approach looks promising, but it requires 2 things. First, we need to prove that restricting ourselves to fragments of length 9 is enough, because we know that we'll get small answer investigating this, but maybe we'll get even smaller answer for some longer fragments. And the second thing is we need to figure out how to quickly calculate the costs of such fragments. And there are also some special cases we need to consider, because in our analysis we assumed that the string is of length at least 9, and it turned out that for some strings of length 7 we could need 5 swaps in order to obtain a correct solution. But if the length of the string is shorter than 9, then we can just calculate the cost of optimal swaps for the whole string. Okay, so now we will show that to get the optimal answer, it's enough to consider fragments of our string of length 9. In fact, we'll show a little bit stronger claim, that is, it is enough to consider fragments of length 8. So let's consider a solution to a given string. In such a solution, we take a set of 3 letters A and use swaps to join them all into one group, and also 3 letters B, which we also join in one group. We showed before that between selected letters A, the only unselected letters can be letters B, and since we cannot have 3 consecutive letters B, between the first and the second selected letter A, there can be 0, 1, or 2 letters B, and similarly between the second letter A and the third one. Therefore, this group looks like this: a letter A, some letters B, 0, 1, or 2, another letter A, then again 0, 1, or 2 letters B, and the last letter A. Similarly, the group for letters B looks the same: letter B, 1, 0, or 2 letters A, another letter B, then again 1, 0, or 2 letters A, and the last letter B. So we know that in the optimal answer there will be 2 such groups of letters, each of length at most 7, and now we would like to investigate how they can be located in respect to each other. So first we assume that the position of the leftmost A is smaller than the position of the leftmost B. If it's not true in our solution, we could just swap the roles of letters A and B in the string. Moreover, let's assume that the groups overlap heavily. That means that the leftmost B is before the middle A. This will be the first case to consider. Since the groups overlap, we can ask what is the smallest fragment that contains them both. We know what happens before the middle A, so let's consider the next letter after it. If it's B, it can be the middle one or the last one, and if it's the middle one, we still can have some letters A followed by the last B. In all cases, the length of the fragment containing both groups is at most 8. On the other hand, if after the middle A we have another A, that must be the last A in the group. So now the fragment containing both groups is of length at most 9, but this is only if we have 2 letters B before the first and the middle A, and 2 letters A before the middle and the last B. The optimal solution uses 2 swaps here, but in order to find them, it's enough to consider a fragment of length 6. In the remaining cases, the length of the fragment containing both groups is of length at most 8. So now let's consider the remaining case, in which the first letter B is after the middle letter A. So either the groups overlap slightly or they are disjoint. Let's denote by alpha 1 and alpha 2 the number of letters B between the first and the middle A, and between the middle A and the last one. And similarly, let's define beta 1 and beta 2 as the number of letters A between the selected letters B. So the cost of joining the selected letters A in a triplet is alpha 1 plus alpha 2, and the cost of joining letters B is beta 1 plus beta 2, and the total cost of the solution is at least the maximum of these two costs. So for simplicity, we will assume that the cost for letters A is at least the cost of letters B. If it's not true in our solution, then we can reverse the whole string and once again swap the roles of letters A and B. Now we will show that we can move the group of letters B to the left, that is, to select another group of letters B with no bigger cost, or to show a fragment of length 8 with better cost. The idea is that we will try to replace B1, B2, and B3 with B0, B1, and B2. If the number of letters A between B0 and B1 is no bigger than the number of letters A between B2 and B3, then we can make this change safely because it does not increase the cost of the solution and it moves the group of letters B to the left. So what if beta 0 is greater than beta 2? Well, it reduces the number of different cases of group B to consider. Moreover, since cost of joining A's must be bigger than cost of joining B's, we have that either the cost of joining B's is equal to 1 or new cost of moving B's is smaller than 3. Because if you had at least 3 letters A here, the optimal cost of moving A's would be at most 1. Taking all these restrictions on the number of letters A between the selected letters B, we end up with only 3 cases. In the first case, we have a fragment of length 7 in which it's enough to make 1 swap in order to get the desired result. So we can stop our search here. In the second case, we also have a fragment of length 7 in which we need only 2 swaps. And we know that the original cost was at least 2, so we can also stop here. The last case is a little bit more complicated and we need to see what is happening before B0. Since before B1 we have at least 2 letters A, then either before B0 we have another A, but then we need only 2 swaps to get the desired result. Otherwise, before B0 we have another B, and before that B we need to have another A. So if the cost of joining A's is 3, then we can achieve this cost here using 3 swaps. And if its cost is smaller, then it cannot use A between B1 and B2. So we can replace the group of B's with B1, B0, and B to the left of it. So in every case, either we constructed a fragment of length 8 with no bigger cost than the original, or we move the group of B's to the left. Repeating this procedure shows that we can always find a fragment of length 8 with the optimal cost. So checking all the fragments with length 8 is sufficient, and for completeness we will show that checking fragments of length 7 is not enough. For instance, we can show a string of length 8 that needs only 3 swaps. But if we restrict ourselves to the prefix of this string of length 7, then we are not able to obtain a group of 3 consecutive B's. And if we consider the suffix of length 7, we would need 4 swaps. Therefore, we need to check fragments of length 8. But the question remains how to efficiently calculate the minimal number of swaps that are needed in short fragments. The idea is to start with a fragment, that is a string of length k, iterate over all possible swaps in this fragment, and see what strings we obtain using these swaps. Then we repeat the procedure for the strings we obtained, taking care not to repeat the same computation twice. Let's see an example with a fragment of length 6. Considering the swap of the first two letters, we obtain another string. Swapping the next two letters produces another one. Swapping the third and fourth letter does not change the string, and we can mark it with a simple loop. Finally, the fourth and fifth letter produce another word, and swapping the last two letters does not change the string. Then we repeat the procedure for all new strings we obtained. But remember that sometimes a swap does not create a new string, but a string that we have seen before. We continue this procedure until no new strings can be added to our picture. So now we can see that this picture looks like a graph. And in fact, if we treat each string as a vertex and each swap joining two vertices as an edge, we have a graph. Now our task is to find a shortest path in this graph, starting from the initial vertex corresponding to the initial fragment and ending in some vertex corresponding to a fragment with 3 consecutive A's and 3 consecutive B's. The length of this shortest path will be the minimal number of swaps needed to produce a desired result. To find such a shortest path, we can use breadth-first search algorithm. In this algorithm, we initialize a queue of visited vertices with the initial vertex, and we give it a distance of 0. Then, while the queue is not empty, we take the first vertex from the queue and analyze all the edges coming from it. Every unvisited vertex is pushed on the queue, and it got distance 1 bigger than the distance of the vertex popped from the queue. And we continue this procedure until we hit a vertex with 3 A's and 3 B's. Then we can stop and return the length of the shortest path. So what is the time complexity of this algorithm? Well, in our graph we will have at most 2 to the power of k vertices, because each vertex corresponds to a string of length k, and each letter in the string can be either A or B. Since for each vertex we need to consider k-1 swaps, we will have at most k edges, and to construct string after swap takes linear time in the length of the string, the total time we spent on traversing the graph will be 2 to the power of k times k squared. Numerically, this value is around 16,000 for k equals to 8. But remember that we need to repeat the search for a shortest path for every fragment in the string. We have n+1 minus k such fragments, therefore the total time complexity of the algorithm will be n times 2 to the power of k times k squared. And since n can be as big as 10 to the 5, this complexity is too big. But you can speed it up using a clever trick. Observe that we don't need to know the shortest path for every possible fragment. We need to know the shortest path among all the shortest paths. Therefore, we can start our search from all of the initial fragments at once and reuse the same graph for all the searches. Thanks to this, our new time complexity will be n times k for creating all the vertices that will initialize the queue, plus 2 to the power of k times k squared for traversing the graph. And this solution will easily fit in the time limit. Okay, so we are finally ready for the implementation. We start from checking the case in which solution does not exist. Therefore, we need to see whether the number of occurrences of letter A in the string is smaller than 3, or number of occurrences of the letter B is smaller than 3. Then we just return -1. Then we test the special case in which one of the triplets already exists in the string. Since we need to consider two cases, triplet of A's and triplet of B's separately, let's make a loop over these cases. And in this loop, the variable A will specify the letter for which we know that there's a triplet, and variable B will denote the other letter, so the letters on which we would like to make a merge. So first we need to check whether we really have a triplet of A's, and if we do, then we need to collect the positions of all letters B in our string. And then we will calculate the best answer by iterating over triplets of positions, and for each triplet we just calculate the position of the third element minus position of the first element -2. And that will cover the special case when we have at least one of the triplets. Otherwise, we'll make a BFS on the graph. We'll define a dictionary in which we'll put the distances for the visited vertices and the queue. Then we'll iterate over all fragments of length 8. For each such fragment, starting in position I and ending in position I plus 7, if this vertex was not visited before, so it is not in the dictionary D, then we are put it in the dictionary with the distance equal to 0, and we append it to the queue. Observe that we didn't put -7 here, so we include some additional suffixes shorter than 8, but this trick will allow us to include the strings of length 7 and 6 into the general algorithm without hurting the overall complexity. Alright, so as long as the queue is not empty, we are taking the first element of the queue and we are removing it, so we say that the queue is one element shorter. And if we find a triplet of A's in this string and a triplet of B's, then we can return the length of the shortest path to this vertex. In our case, we will iterate for all the swaps in this string, and we perform each swap. So we will swap the letter on position I with the letter on position I plus 1. And since in Python the strings are immutable, we need to construct totally new string. And if this new string was not in the dictionary, so it was unvisited, then we will say that the distance to this new string is 1 bigger than the distance to the string W, and we append this string to the queue. All right, let's run the code on the sample test cases. It passes them, and in fact, this program will get 100 points when tested by Codility servers.